Welcome to part 3 of my series on Large Eddy Simulation. In the last two parts of this series, we had a look at the turbulent kinetic energy. We had a look at the subgrid scale turbulent kinetic energy and the resolved turbulent kinetic energy, and we used these two quantities to assess the quality of our large eddy simulation. And it's a really good place for us to get started because we can carry out a large eddy simulation and quickly assess whether we think the LES simulation that we've done is any good. Now, we've left quite a few theoretical points untouched so far, and those are the theoretical points I'm going to move on to now in the next few videos in this series. So in today's talk specifically, I'm going to start looking at the subgrid models for LES. And you may have come across these when you're setting up your large eddy simulation and you have to select which of the subgrid models do you want to use. Do you want to use a Smagorinsky model, for example, or do you want to use something a bit more complicated? Well, in today's talk, what I'm going to give you is the basic understanding of the subgrid models, why they're needed and exactly what they do. And then after this talk, in the next few, I'm actually going to go on to review individual subgrid models so that you get an understanding of the differences between them and perhaps which ones you should select for your LES application. So sit back, take some notes. There's some really great points of understanding in this talk, which I know are going to really help you understand and interpret your LES simulations. So here we go. So before we get started with this talk, I just want to make a few notes before we begin. And the main thing to note before we begin with this talk is the point is to develop a conceptual understanding for the subgrid modeling that goes on in implicit LES and why we need the subgrid model. Now, the reason I've chosen to do this is that, of course, in many talks that you'll see on the internet and in papers and textbooks, the focus of the subgrid model tends to be on the mathematics of the filtering operation and how we actually derive subgrid models. And that's not going to be the focus of the talk today because I want to help you develop an understanding. And once you've developed that understanding, you can then go and consult those resources and look into the mathematics of filtering and other processes in more detail. And I'm also not going to be talking about specific subgrid models yet because I want to go through subgrid models first in general, and then I'm going to look at specific subgrid models after we've got a generic understanding for what they are and how they work. So models like the Smagorinsky model, I'm going to present those in a later talk. So first, just to start with a bit of background to help you understand where we are and what we're thinking about today. Now, what we're going to do is start thinking about turbulent eddies. Now, if we think about a turbulent flow that's comprised of a number of eddies, if we think of the larger eddies, these eddies are unstable. They're inherently unstable by themselves. And what that means is, of course, is that they can't continue to exist as they are. They're not stable and they'll want to break down. And of course, the larger eddy will break down into smaller eddies, which themselves will continue to break down into even smaller eddies. And this process all comes from the fact that the eddies themselves are unstable. And the process by which eddies break down and continue to break down, you'll often see referred to as the eddy cascade or the energy cascade. But for now, all we need to care about is that the eddies themselves are unstable and this causes them to break down. Now, the breakdown process, of course, continues. The eddies get smaller and smaller and they continue to break down until we reach the smallest eddies, which are dissipated into heat by the action of molecular viscosity. So we have this cascading action of the large eddies continuing to break down into smaller and smaller eddies until they're small enough that those eddies are then affected by molecular viscosity, which dissipates that energy into heat. So this is the overall energy cascade process that's going on with the turbulent eddies. And it's very important that we bear this in mind because it will help us to understand what's going on with the subgrid model and why we need it in LES. So what I want you to do now is, now that we've thought about how eddies in a turbulent flow work, have a think about how eddies are represented on a grid. That could be a CFD mesh or another numerical solver. If we think of an eddy, you've seen this in a few of my talks before, we can represent an eddy on a mesh with something like the diagram which you see here. Now in most CFD solvers, of course, each cell or element in the mesh is going to store and calculate one value at the centroid, and then there's going to be a linear variation across that cell and between cells. So what that means is that on a grid of cells, we can represent an eddy using velocity vectors. We'll have a sort of a swirling motion, which will look like something you can see in the diagram. And of course, if you have a mesh of a given size, you can capture and represent a range of different eddy sizes on that mesh. And the image you see there, we've got velocity vectors, which are put at the cell centroid, where we've calculated the velocity value. And you can see we've got the large eddies there, which we're able to represent on the mesh. And as they get smaller and smaller, eventually we get to the point where the physical eddies that exist in our turbulent flow are smaller than the size of one of the cells on the mesh. And this is very important for us because if we're only calculating and storing one value in a cell, whether that be at the centroid or at the node, it means that within that cell, we don't have enough values to capture or represent that swirling flow field. And so what that means is that the mesh is limiting the size of the eddy that we can physically represent on the mesh. And in the diagram, you can see there, I've got the mesh on the right-hand side. That small eddy, we're not able to resolve it. It physically exists in the flow field, but the CFD mesh isn't able to capture it and represent it for us in our solution. And so what does this mean? We're now going to combine the thoughts of the energy cascade and the representation of eddies on a mesh, and this leads us to a very interesting observation. And that is, if we remember that the eddies themselves are unstable and they want to break down. So in the image on the left, you can see there we've got that large eddy on our section of mesh, and it wants to break down. And one of the eddies it wants to break down into is given in that second image there. And the CFD mesh is able to represent this breakdown process physically because it's able to represent the size of the eddy that it's getting broken down into. But now if we look at the diagram on the right, this is the very important thinking point. We can see that that eddy on the left, which is captured by those 4 cells, it itself is unstable and it wants to break down. However, it can't break down in this case because the eddy that it wants to break down into, we're not able to resolve it on the CFD mesh. That's the very important thinking point that I want you to think about with these subgrid models, is that the eddy wants to break down, but the size of the eddy it wants to break down into is too small, and so we can't capture it on our mesh. So we're going to have to do something about this. Now, this creates a problem for the CFD solver, and the reason what happens is that eddy that's about the size of 4 cells, for example, in this example, it's just bigger than the size of the cell size. It wants to break down, but it can't because we haven't got a small enough cell size to represent the eddy that it wants to break down into. Now remember, we have the action of that other force acting on the eddies. We've got the molecular viscosity, and normally for our very smallest eddies, that molecular viscosity is strong enough to dissipate the energy of the smallest eddies into heat. But for our case in LES, the smallest eddy that we've got, molecular viscosity isn't strong enough to be able to break down that eddy. And so what does that mean? If we can't break it down, well, the eddy on our CFD mesh will persist and it will stay in our mesh for a long period of time. And of course, what that means is if we look at the overall kinetic energy of our turbulent flow, it's too high. We've got too much turbulent kinetic energy because the smallest eddies on our mesh are not able to break down. They're just existing for a long period of time without being broken down. So what does this tell us? What do we need to do if conceptually in our large eddy simulation to fix this problem? Well, what it means is that those eddies which are just larger than the size of the cell, in this simple diagram I've got for you here, just those 4 cells, so that size of eddy, we need a method of breaking down that eddy and removing it from the flow, because it's not able to break down because of its instability, but also molecular viscosity is not strong enough to break it down. So we've got to come up with some kind of a method that we can take that eddy and get rid of it from the mesh so that our kinetic energy of our flow is brought down to the correct level. And the method that we use to do this is by increasing the turbulent dissipation rate. And don't worry if you don't fully understand what that means at the moment. I'm going to go into a lot more detail so that you understand what it means. But so far in the talk, the key point that you need to take away is that these eddies, which are just larger than the mesh size, we need a method of removing them from the mesh to bring down our turbulent kinetic energy. And as I've said, we're going to be doing this by artificially increasing the turbulence dissipation rate. That's the method that we're going to use to remove and take out these small eddies that can't be dissipated. And I imagine for some of you, you may not be very confident with the idea of turbulence dissipation rate. So I'm just going to do a quick 1 or 2 slides to bring you up to speed so that you know what we're talking about here. Well, overall, epsilon, or the turbulence dissipation rate, this is one of the quantities which you solve for in the K epsilon model, for example. This is defined as the rate that turbulent energy is converted to thermal energy. So if you think of that diagram of the smallest eddies, it's the rate that the turbulent energy in those small eddies is converted into heat. And what does that mean as a quantity? Well, it's a rate. It's going to be a turbulent kinetic energy per unit time. It's the rate that the turbulent kinetic energy is dissipated. So if you've ever looked at your CFD solution and you've looked at the quantity epsilon, what you'll notice is that it has units of meters squared per second cubed. And why is that? Well, physically, turbulent kinetic energy has units of meter squared per second squared, and we want the rate, or the time that that energy is dissipated in. So we divide by the units of seconds, and this is why epsilon has units of meter squared per second cubed. And it's important that we have a good idea of this turbulence dissipation rate, because that's what we're going to be thinking about with regards to our large eddy simulation. And so what does it really mean? Just taking this thought a little bit further, well, if we have a given turbulence dissipation rate, say, then our eddies will take some time to dissipate into heat. Those are our smallest eddies. The eddies will exist and propagate through the flow for some time and then eventually dissipate into heat. But if we were some reason to increase that dissipation rate, what we would find is that eddies of a given size are dissipated faster. So the eddies are propagating for a short length of time and then they're dissipated because the dissipation rate is much higher. That's what we need to be thinking about with the quantity epsilon. And it also means, of course, that we're able to dissipate some eddies which have slightly higher energy in the same period of time. So that's what really we're thinking about with the turbulence dissipation rate. But how is the turbulence dissipation rate calculated? Well, if we think of a real turbulent flow or a DNS simulation, for example, the equation that you want is given there in equation 2. We see that the dissipation rate is given by the molecular viscosity multiplied by the velocity gradients in the flow squared, or multiplied by themselves. Of course, there'll be a proper tensor operation if you consider the full velocity gradient tensor there. But for the moment, we don't really need to think about that. Conceptually, what we need to just think about is that the turbulence dissipation rate is just given by the product of the molecular viscosity and the velocity gradients in the flow. And what is that telling us? Well, of course, we expect to see the molecular viscosity in there, because if we have a fluid with a much higher molecular viscosity, it will be able to dissipate that turbulent energy of the smallest eddies much faster. So we've definitely got the molecular viscosity in there, and we've also got those 2 velocity gradients. Now, of course, for a real turbulent flow, this is the velocity gradient of the true velocity containing the fluctuations. So this is why, if we're solving a RANS turbulence model, we often solve a transport equation for epsilon, because remember, we don't really know what that true velocity is in our RANS calculation. But of course, we're looking at LES now today. That was just a small side point. So now, if we just think about the turbulence dissipation rate in a bit more detail, what we can see and what we can understand, of course, is that the molecular viscosity is very small. So in comparison with the energy of the flow, the molecular viscosity is very small. So if we look back at equation 4, what does that tell us? Well, it tells us that actually, if we want to dissipate turbulent energy, we need quite high velocity gradients. And now what I want you to do is to zoom in and think a little bit about a turbulent eddy. And I've got a small diagram for you on the slide to help you understand this. If we've got a very large turbulent eddy, then the dx, or the distance over which the velocity changes, is quite large, and that means that velocity gradient is quite small. So if we just look at equation 4 there, that tells us that for a large eddy, the molecular viscosity is low, the velocity gradient is low, so actually those eddies aren't going to be dissipated very fast at all. But of course, as our eddies get smaller, the velocity gradient increases, And if we look at equation 4, the molecular viscosity has changed the same, but for our very small eddies, we have a very large velocity gradient. And so the product of those two quantities gives us a high dissipation rate. And this is exactly why the molecular viscosity is only able to dissipate those smallest eddies at the end of the energy cascade. It's because the small eddies have a very high velocity gradient, and they need that because the molecular viscosity is very low. So now we've thought a little bit about turbulent dissipation rate and how we dissipate eddies. Let's jump back now to think about our LES simulation that we've got. And remember, we've got the problem of those eddies which are just larger than the grid size, the cell size, and we need to find a way of removing these eddies from the flow. And of course, what we see is that these eddies are a lot bigger than those smallest eddies which are dissipated by molecular viscosity, because their distance is much larger, the distance across the eddy, and therefore the velocity gradient is currently too small. So for these eddies, we can see the velocity gradient is currently too small for them to be dissipated by molecular viscosity. What can we do to make sure that we remove these eddies from the flow in our LES simulation? Well, we can actually make a very simple change, which is to increase that viscosity. So of course, in a real turbulent flow or a DNS simulation, we've only got the molecular viscosity, nu, or mu if you want to use it, multiplied by density. But in LES, what we're going to do is we're going to increase it from nu to mu plus an additional contribution, which we're going to call the subgrid viscosity, nu SGS. And of course, what that allows us to do, because we've increased the viscosity, the dissipation rate is also going to increase. So if you look at equation 5, the dissipation rate, epsilon, is now increased because we've got this additional contribution, nu SGS. And so overall, when we're thinking about large eddy simulation and we're trying to understand it, equation 5 really tells us what we're trying to do when we do it. We're trying to increase the dissipation rate, and we need to be very careful because we want to increase the dissipation rate just enough so that we can dissipate those eddies which are just larger than the mesh size. So we want to target those eddies and carefully increase the dissipation rate by increasing our subgrid scale viscosity so that we can remove those eddies from the mesh. But there's one last thinking point which we need to think about here before we jump into some further detail, and it's actually to understand what we're really doing here. And this is a very careful point, and it might be worth taking a minute or two to think about what we're actually doing here. So what we're doing is we're increasing the dissipation rate artificially in our LES simulations, and this will cause the eddies that are just larger than that smallest cell size to dissipate and to break down. So we're dissipating the eddies. Of course, this isn't the true process. What we're actually doing in LES is we're artificially increasing the dissipation rate to mimic the breakdown process. And that's a very important point to think about when you're doing large eddy simulation, is that those eddies, they want to break down because they're unstable in the energy cascade, but they can't do that on the mesh. And so what we do is we do something, we cheat, and to mimic that breakdown process that we can't do, we increase the dissipation rate instead. And that's probably the most important thinking point of this whole talk, and it's useful to help get your head around. But then if we go back to our CFD solution, what will happen? If we look at the situation on the left, this is the situation where if we don't have a subgrid scale model, for example, if we just ran the calculation without any LES modeling, those smallest eddies would just perpetuate on the grid, and they would break down eventually, but it would be far too slow, and that would mean that the kinetic energy is too high. But if we take the scenario on the right, we artificially increase that viscosity through the subgrid viscosity, and what that means is we can dissipate those smallest eddies to mimic the breakdown process. So fantastic. At this point, you should probably have a better idea of what the subgrid model in LES is actually trying to do. But there's a very subtle point here which some of you may have picked up on at this stage, and that is, in large eddy simulation, of course, we're not solving an equation for epsilon, the dissipation rate. That's something we do in a RANS model. We solve for the K epsilon model, for example, or K omega or something different. But in LES, we're not solving an equation for epsilon. So what do we actually do in the LES equations? Because we still need to break down these eddies. We need to dissipate them from the domain. But what's the method that the LES equations actually do, and how is this actually incorporated into the CFD algorithm? That's the bit we're going to look at next, now that we've got this conceptual understanding. So now looking at increasing dissipation in LES, how do we actually do it in terms of the equations? Well, the easiest way to understand this is to start with the Navier-Stokes and continuity equations, which I've got for you there on the slide. And these are the full Navier-Stokes and continuity equations that you would have in a DNS calculation, for example. These are the actual equations that govern the fluid flow. And as far as understanding the manipulation that we do in LES, what we need to focus on is we need to focus on the viscous stress term, which is underlined there in equation 7. And this is on the right hand side, and what you can see, we've got the divergence of the viscous stress tensor. And what this term does in a fluid flow, this is the term that's responsible for dissipating energy through molecular viscosity. So if we remember that process that we talked about before, the molecular viscosity is breaking down the smallest eddies and dissipating them into heat right at the smallest scales in the flow. And that's the term physically in the equations that controls that process. But remember, in the real flow, this dissipation is not strong enough to dissipate those eddies that are just larger than the grid size. So just intuitively looking at equation 6 and equation 7, we would expect that we need to do something to the viscous stress term in equation 7 so that we can artificially increase it a bit. And that's what we're going to do for the LES equations. And the most straightforward way to do it, and this is what you'll see in the majority of papers, is we add an additional stress term there to that viscous stress tensor. And this term is often called the subgrid stress, and we're adding this, it's going in the divergence operator again, as we saw before. And remember, the purpose of this stress term is we're going to artificially increase the dissipation so that we're able to dissipate those eddies that are just larger than the cell size. And of course, it's worth noting here that I've just presented this method of approach from an intuitive and conceptual understanding. You can do this rigorously and mathematically if you look at the filtering processes, but I'm not actually going to go through that in the talk because I don't think it's useful for what we're trying to do here. But you still arrive at the same point as you do with equation 9 there. You've got that extra term for the subgrid stresses. Now, I thought it would also be worth just making a quick note for what the subgrid stress actually is so that you can help understand it when you're looking through the papers and looking through references for LES. Now, the way to think about this is if you think about your CFD mesh, for example, on the left, you'll have a variety and a number of different eddies which are smaller than the cell size. These are going to be all over the place. They're going to have different sizes. And these eddies, we can't resolve them in the CFD calculation, but they still exist there physically on the mesh. And what do these eddies do? Well, actually, the action of the eddies is to provide a resistive force or a resistive stress on the eddies and the flow that we do resolve. So these eddies, even though we can't model them directly as eddies, we can still model the force or the stress that they exert back on the main flow that we do model. And in a way, you can think of this as an application of Newton's second law with an equal and opposite reaction force, for example. That's another way of thinking about it. And so what we're doing is we're not modeling the physical eddies in the velocity field, but we are modeling the stress and the force that they exert. And this is the force that will dissipate and break down those eddies that are just larger than the grid size. Because of course we have the cascade, so they will. And the way that this stress is calculated mathematically is often using what's called an eddy viscosity model. And I've put the equations for you there on the slide in equation 10. And at a first glance, these terms do look quite complicated. There seems to be a lot going on there with a lot of interesting notation all over the place. And what I've decided to do is to go through these eddy viscosity models in a bit more detail in a separate video, which should be coming out shortly after this video. So if you're interested in equation 10 and actually where it comes from, how it's used in RANS and in LES, it's worth going and checking out that video if you want to actually see the mathematics. But for now, in understanding our subgrid models in LES, we don't need to jump into too much detail in this equation. The only thing really to focus on here is if you look at the left-hand equation in equation 10, you've got that the subgrid stress, tau, is going to be equal to some term 2 times the density, and you've got the subgrid viscosity there, nu SGS. That's what we talked about before, and then multiplied by the deviatoric part of the strain rate tensor. Again, this looks quite complicated, but for now, all you really need to think about is you can see we've got some velocity gradients there. And remember, of course, that as the eddies get smaller, the velocity gradient increases. And what this tells us, of course, is that in the CFD solver, in the CFD code, as the eddies get smaller that we're resolving, that velocity gradient is going up. And that also means that the subgrid stress and the subgrid force is also going up. So by the time we reach that smallest eddy that's just larger than the grid size, this subgrid force is going to have increased enough that we can dissipate and break down that eddy. So that's really what we're doing here, is that we're applying a force and a stress that's proportional to the velocity gradient of the resolved eddies. And we've also got the subgrid scale viscosity, which we introduced earlier in terms of the dissipation rate. And that's really all you need to think about at this stage for the subgrid stress, is that the subgrid stress is going to increase depending on that velocity gradient. But of course, the natural point to think about now is what about this subgrid viscosity? So that's nu SGS. Because really what this is, the nu SGS, is this is the factor that controls the strength of the stress that we apply. If nu SGS is too high, we're going to break down the eddies in our turbulent flow and the kinetic energy is going to drop too low. But if we have no subgrid viscosity, or if it's too low, the subgrid stress is going to be too small and we're not going to be breaking down those eddies that are just larger than the grid size. So the way I want you to think about it, and the way that's useful to think about it, is that the subgrid viscosity is really just the control that we apply to that subgrid stress so that we can target and break down the eddies we want. Think of it as the controller. And now we of course want to make some progress in defining and calculating this subgrid stress, this control. How do we do that? Well, the first conceptual point that you want to think about with the subgrid stress is to think about the eddies themselves that are smaller than that cell size. And of course, in a real turbulent flow, we expect to have a variety of eddies. We'll have some really small ones, some slightly small ones. They'll be in different positions all over the place, even though they're just smaller than the cell size. And the key assumption that we make when we're developing a model for the subgrid viscosity is to assume that the eddies are isotropic. And I really wanted to just hammer home this point on this slide because I think it's important to think about what does this actually mean in the context of developing an LES model. Well, of course, isotropic means that something is the same in different directions, but in terms of eddies, what that means is that it means that the eddies all have the same shape. That's really the way you should think about it, is that smaller than that cell size, we're going to have eddies with a variety of different sizes, but they'll all have the same shape. And I think the diagram on the slide there helps to really think about this process. We could have anisotropic eddies like you see in the right-hand picture, but the key assumption with the subgrid models is that the eddies are isotropic. And the reason it's an important assumption is we only need to consider the eddy size. We don't actually need to consider its shape. And you can think about this, you could take one value or a single scalar parameter, and that could tell you the size of the eddy, say its diameter or its volume or its cross-sectional area, for example, and you wouldn't need to think about the shape. You don't need to think if it's an ellipse, for example, or if it's a perfect sphere or circle. We're making the isotropic assumption, which means we only need to think about the eddy size, and this makes the models a lot easier to develop. And as I just alluded to there on the previous slide, as the eddies are isotropic, our subgrid scale viscosity, nu SGS, we can get this to be a single scalar value. So we can make it very simple and easy to calculate. We don't need it to vary depending on eddy size, for example. It's only going to take a single value. And this will tend to be important later when we think about how the eddies interact with walls, because of course, as we approach the walls, we may expect the eddy size to change, for example, but actually the assumption we're making here is that the eddy shape stays the same, it's just the overall size of the eddy stays the same. And the way I tend to think about this intuitively is that if you have cells and within those cells you've got eddies that are larger, that would mean that your subgrid viscosity is larger. So really the subgrid scale viscosity is giving you an indication of the size of the eddies that are contained within the cells in your CFD mesh that you haven't modelled. And the take-home point from this slide, of course, is that there are a variety of different methods for calculating this subgrid scale viscosity. And you may have seen some of these before. There's the Smagorinsky model, for example. You've got the WALE model, the Wall model, LES model, dynamic models. There are a variety of different models you can use for calculating the subgrid scale viscosity. But they're all working on the same principle that the eddies within the cells are isotropic. They have different sizes, but they have the same shape. So we're going to only need a very simple model to calculate them. And I'm going to go and look through those models in a bit more detail in a separate video. But let's just have one final thought about the subgrid viscosity before we end the talk. And let's think about what this parameter might depend on. Well, we can actually intuit and just work out some sensible parameters that the subgrid viscosity will depend on just by thinking about what we need it to do. What I want you to do is think about now two CFD meshes. So you're running an LES simulation and you've got a fine mesh and you've got a coarse mesh. You've got two different meshes. And we need the subgrid model to break down the eddies that are just larger than the cell size. So you can see in the fine mesh on the left on the slide there, that smallest eddy that we need to break down is actually quite small. But if we now move to our coarser mesh, we can see that the smallest eddy we need to break down is actually a lot larger. And that means that we'll need the subgrid viscosity to be larger in the coarse mesh than it is on the fine mesh, because the function is to break down the eddies that are just smaller than that largest cell size. And so that leads to the very important conclusion that the subgrid viscosity, no matter how we calculate it, is going to be a function of the mesh size. So your subgrid viscosity is going to be different depending on if you've got a coarse mesh or a fine mesh. The subgrid viscosity needs to be a function of the mesh size. And at this stage, and I haven't mentioned anything yet about how you might do that, whether you might take a cube root of the volume, for example, I'm going to leave that to a separate talk. For now, all we need to think about is that on different meshes, the subgrid viscosity will be different. It needs to be stronger when our mesh is coarser. And so this leads to a very interesting conclusion, which is actually that in LES, when we change the mesh, we're actually changing the equations and the subgrid viscosity that we use in each calculation. And so that may take you a little while to get your head around, but if you compare that to a RANS calculation, for example, as you change the mesh, the equation that you'd use for the RANS eddy viscosity, for example, stays the same, but just the resolution of the field changes. And this leads to a very interesting conclusion, which is you can't do a realistic mesh independent study for LES, because when you refine the mesh in an LES calculation, the subgrid viscosity that you need to break down those smallest eddies reduces. So the equations change each time you change the mesh. And this is the practical reason why we actually use that different criteria for LES, where we say that a good LES calculation is an LES calculation that resolves 80% of the turbulent kinetic energy. We don't do a mesh independent study with LES. And this is really the reason why, is that actually each time we refine the mesh, we're solving a different set of equations when we do that. So now just to wrap up the talk with some of the key conclusions to remind you of what we talked about today. The overall principle of LES and the way we can think about it is that we have a variety of eddies in our turbulent flow, and those eddies are unstable and they want to break down. Now, this leads to a problem on our CFD mesh because eddies that are just larger than the smallest cell size can't physically break down. And what that means, if we run the calculation, those eddies will persist on the mesh for too long and they won't break down. And that means that the turbulent kinetic energy is too high and we'll get the wrong solution. And so what do we do to account for this? In LES, we increase the dissipation rate artificially, and what this does is it allows us to mimic the natural breakdown of eddies that would occur at the mesh limit. And we're mimicking the breakdown by increasing the dissipation rate. They're different things, but they have the intended effect of removing those eddies from the mesh, so we get the right turbulent kinetic energy. And the way that we control this process is through the subgrid viscosity. That's new SGS. And at the moment, we haven't said anything about how we're going to calculate this subgrid viscosity. All we know is that it's going to control the subgrid stress, and a larger subgrid stress will break down larger eddies. And the final point to note is that we know just by thinking about a large mesh, a fine mesh and a coarse mesh, the subgrid viscosity is going to be a function of the mesh size. And that's very important because larger cells will need a higher subgrid viscosity so that we can break down the eddies that are just larger than that cell because they're a lot larger. So that brings me to the end of the talk. I really hope you guys are enjoying this series of talks that I've been giving on Large Eddy Simulation. I'm definitely really excited to get onto the next few talks where I can actually start to look at those subgrid models in more detail. And then, of course, many of you have been asking in the comments section, once we've looked at the subgrid models for Large Eddy Simulation, then particularly we can move on to look at more intricate and detailed models, perhaps that combine some aspects of RANS and LES together. So some things like the SAS SST model, for example, we can move on to look at those after we've looked at the LES models in more detail. So I really hope you're enjoying these talks so far. Please keep watching. I know you're going to continue to find lots of value in these talks. And it's worth also me just pointing out that the bit of maths which I did glance over quite briefly is the eddy viscosity formula for the subgrid stress. And if you're interested in how that's derived and put together, I'm going to do that in a separate talk. So don't worry, keep watching, and that talk will be out soon. Until next time, thank you all very much for watching, and I hope you enjoyed the talk.